Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the communication systems previous year questions of the IES or ESE electrical engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel and don't forget to press the bell icon button. So whenever we upload a new video, the direct notification comes from while. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to discuss about the one question. See the question here. In a communication system, a process for which statistical averages and time averages are equal is called. So in a communication system, they are asking in which process the statistical averages is equal to time averages. Option A stationary process, option B ergodic process, option C Gaussian process, option D bibostable process. So out of the four options, option B, ergodic process is the correct solution of this question. So let's discuss something more facts about this one. So in communication system, basically there are three processes. The first process name is stationary process, and the second one is wide sense stationary process, and the third one is ergodic process. So basically the stationary process is nothing but here, if any random process is said to be stationary process, if all the variables like mean square, variance and autocorrelation, when all the statistical values are independent of time, then only we say that particular process or that particular random process is said to be a stationary process. So a stationary process is nothing but here, if any random process, it is said to be a stationary process when all the statistical values like mean square, variance and autocorrelation, when all these are independent of time, then that random process is said to be a stationary process. And similarly, the wide sense stationary process is nothing but any random process is said to be a wide sense stationary process whenever the statistical values like mean and autocorrelation are independent of time. So whenever these two things, mean and only autocorrelation, only these two things which are the mean and the autocorrelation, means autocorrelation is r(x) of tau. So r(x) of tau, when these two are independent of time, then only we say that is called as a wide sense stationary process, whereas the autocorrelation is also a function of the difference of the time, but it is a function of difference of the time, but not a particular independent time value, but it is a function of difference of the time. So therefore we can say if any random process in this, the statistical values like the mean and the autocorrelation are independent of time, whereas the autocorrelation is a function of difference of time, then that process is said to be a wide sense stationary process. And the third process is called as a ergodic process. The ergodic process is nothing but here, in any random process is said to be a ergodic process whenever the statistical average is also called as the ensemble average. So whenever the statistical average or the ensemble average is equal to time averages, then we say that process is said to be a ergodic process. So basically in our question they have asked a random process in which the statistical averages is equal to time averages, that particular process is called as a ergodic process. So this is the correct solution of this question. So now we are going to discuss about the 102nd question. So the question here, which one of the following statement is correct? Noise has the greatest effect in a communication system when it interferes with the signal. So noise has the greatest effect in the communication system when it interferes with the signal. In the transmitter, in the channel, in the receiver, in the transducer. So basically whenever the signal is going to transfer from the transmitter to receiver, there is a channel. So therefore in the channel there is a high possibility or high probability of occurrence of the noise. So option B is the correct solution of this question. So let's discuss something more about this one. So whenever a signal is going to transmit from the transmitter to receiver, in this region this is called as a channel. So in this channel there is a high probability of noise is going to have a highest probability of its effect in the channel, but not in a transmitter or not in the receiver, but the noise is going to have the greatest effect in the communication line whenever a signal is going to transfer in this channel. This is called as a channel. So this is a noise. This noise is going to have the highest effect on this channel whenever the signal is going to transfer in this channel from transmitter to receiver. So basically noise is categorized into two types, which are the external noise and the internal noise. External noise is again characterized into two types, which are the atmospheric noise and the man-made noise. So man-made noise is also called as the industrial noise. So due to atmospheric noise, it is due to the solar noise because of the sun rays and because of the extraterrestrial noise due to to some other factors. So because of these two are under the category of the atmospheric noise, and this is the man-made noise. So basically external noise is going to have the highest effect when compared to the internal noise. So this is the internal noise is again characterized into some types, which are the transit time noise, thermal noise, flicker noise, partition noise, and the short noise. So basically this transit time noise is nothing but here at high frequency, whenever the frequency is very high, at the particular frequencies the input itself is going to act like a noise. That is called as a transit time noise. And this thermal noise is because of the temperature. So flicker noise, due to impurities present in materials. So whenever the impurities are going to present in the material, this also going to produce a noise. That noise is called as a flicker noise. And similarly partition noise, this noise is going to occur at the junction of the devices. So because of the junction of the devices, there is a particular noise which is going to produce, that is called as a partition noise. Whereas the short noise, this is due to discrete nature of the electronic emission. So whenever there is a discrete nature of the electronic emission, the noise is going to arise. That noise is called as a short noise. So I have categorized into all these belongs to the internal noise. So these are the noise which are going to affect the signal whenever it is going to transfer from the transmitter to receiver in the channel. So basically the noise is going to have its highest effect or highest probability of its effect on a signal whenever it is going to pass through a channel. So basically we can say finally the noise is going to have its highest effect on a signal when the signal is going to transfer in this channel. So now we are going to solve the 103rd question. See the question here. A sinusoidal signal with a random phase is given by x of t is equal to s sin 90 minus 2 pi f t plus theta with the probability density function. The probability density function is 1 by 2 pi for 0 less than or equal to theta less than or equal to 2 pi, and it is 0 otherwise. So what is the maximum amplitude of the autocorrelation function of this signal? So basically for this x of t, we have to figure out what is the autocorrelation function, and then we have to find what is the maximum value of this autocorrelation function we have to figure out. So what are the four options? Option D, which is a square by 2, is the correct solution of this question. So let's solve this numerical. So in the question they are given a message signal x of t is equal to a sin 90 minus 2 pi f t plus theta. So basically if you see carefully, this is sin 90 minus anything is again sin theta. So I am assuming this is x. So sin 90 minus x is again cos x. So therefore cos x is 2 pi f t plus theta. So this x of t is going to simplify into in this fashion, which is a cos 2 pi f t plus theta. So now they also given the probability density function, which is probability density function p of theta is equal to 1 by 2 pi for region of 0 to theta less than or equal to 2 pi. So the theta is going to lie between the 0 to 2 pi, the value is 1 by 2 pi, and in remaining other region its value is 0. So therefore this is the diagram of the probability density function. For 0 to 2 pi its value is 1 by 2 pi, and remaining all of the theta its value is 0. So now we have to find what is the autocorrelation function. So this is the autocorrelation function. The basic definition of the autocorrelation function is expectation of the x of t into x of t plus tau. So basically expectation of x. So basically expectation of x formula is integration x is equal to minus infinity to plus infinity x into probability density function f of x into dx. So this is the standard formula. So if you see carefully here, f of x is called as a probability density function, but here I am going to replace with another variable which is p of theta. So therefore f of x has to be replaced with p of theta, because in this question they are given p of theta is the probability density function, but generally we have to take care f of x. So if you see carefully here, x in place of x we are going to use x of t into x of t plus tau. So wherever x is there, x, so you have to replace with x of t into x of t plus tau. Here f of x has to be replaced with p of theta. P of theta, here we are going to do integration with respect to theta. So therefore theta is equal to minus infinity to plus infinity. So theta is equal to minus infinity to plus infinity. Now we have to solve this equation. Then we are going to get the autocorrelation function, and then we have to find what is the maximum value of the autocorrelation function. So we know the value of x of t. X of t is a cos 2 pi f t plus theta. So now we have to find what is x of t plus tau. So in place of t we have to replace t by t plus tau. So therefore here we have to replace t by t plus tau. So x of t plus tau is nothing but here this is the thing we are going to get. Now we know the value of x of t, we know the value of x of t plus tau, and we also know the value of the p of theta. So substitute everything. So if you see carefully, one more interesting thing is here, theta is equal to minus infinity to plus infinity, but here theta is going to have this p of theta is going to have non-zero value only from 0 to 2 pi. So therefore this all this integration is going to converge to only integration 0 to 2 pi, because remaining all other values it is 0. So this integration is going to converge to theta is equal to 0 to 2 pi. So theta is equal to 0 to 2 pi. We know the value of x of t. We know the value of x of t plus tau, and the probability density function in 0 to 2 pi is 1 by 2 pi into d theta. So here a into a is become a square by 2 pi. So a square by 2 pi, I am going to take it outside of the integration. Then the remaining thing is cos 2 pi f t plus theta and cos 2 pi f of. So I am going to do the multiplication inside. So then I am going to get 2 pi f t plus 2 pi f tau plus theta into d theta. Now I have to do the integration for this one. So this is cos a into cos b. So basically cos a into cos b is equal to cos a plus b plus cos a minus b by 2. So basically cos a into cos b is equal to cos a plus b plus cos a minus b by 2. So I am going to use this thing here. So this is cos a into cos b. I am going to assume a is equal to 2 pi f t plus theta and b is equal to 2 pi f t plus 2 pi f tau plus theta. So here, so 1 by 2. So 1 by 2 into 2 pi is equal to 4 pi. So the a square by 4 pi. This is cos a plus b. So this you have to add with this one. So 2 pi f t plus 2 pi f t, 4 pi f t, theta plus theta, 2 theta, and there is only one 2 pi f tau, 2 pi f tau. Now plus cos a minus b. So a minus b is nothing more this minus this. 2 pi f t, 2 pi f t get cancelled, theta get cancelled. The only thing is 2 pi f tau, 2 pi f tau. So now you have to do integration with respect to d tau. So now integration of cos is nothing but sine. So integration of cos is again sine, but we are going to do integration with respect to only theta. So therefore theta is the only thing variable and remaining all other the constants. So now it is going to become 2 in the downward direction in the denominator, plus integration of cos is again sine. So integration of cos is, here cos is a constant. See here we are going to do integration with respect to theta. So therefore it is a f and tau are independent variables or constant values. So therefore this is stated as a constant. So because it is a not function of any theta, so therefore it is a constant value. So integration of any constant is equal to integration of any constant into d theta is equal to k into theta. So here k is cos 2 pi f tau. So therefore cos 2 pi f tau into the integration is with respect to theta. So therefore you have to make theta. So substitute the limits 0 to 2 pi. So now we have to further simplify this one. So now we have to substitute the limits. Theta is equal to 0 and theta is equal to 2 pi. So upper limit minus lower limit. Upper limit is theta is equal to 2 pi. So wherever theta is there, you have to substitute the 2 pi. So 2 into 2 pi is nothing but 4 pi. So remaining everything is same except 2 theta I am going to replace with 4 pi and remaining everything is same. Now here also theta has to be replaced by 2 pi. So into 2 pi minus of, now you have to substitute the limit 0. So whenever theta is equal to 0, when theta is equal to 0, 2 into 0 is again 0. So the remaining things are going to present. So sine of 4 pi f t plus 2 pi f tau by 2, and this is cos into anything is 0. As theta is 0, anything into 0 is again 0. So plus 0, I have written here plus 0. So now if you see carefully, sine of 4 pi plus anything, sine of 4 pi plus anything. So sine of 4 pi plus x is again is equal to sine x. So therefore here sine of 4 pi plus anything is equal to sine x, means you can replace with this one like this. So plus. So if you see carefully, again these two are same. This sine 4 pi f t plus sine 2 pi f tau by 2 is equal to minus of this thing. So plus and minus are going to get cancelled. So these two are going to get cancelled. So the only thing which is going to present in this bracket is cos 2 pi f tau into 2 pi. So therefore a square by 4 pi into cos 2 pi f tau into 2 pi. So pi get cancelled and this is 2 ones are 2 2s are. So finally we are going to get a square by 2 cos 2 pi f tau. So finally we have figured out the autocorrelation function of the x of tau is a square by 2 cos 2 pi f tau. It's a function of tau. So therefore if you see carefully, the amplitude itself is called as a maximum value. For sine and cos, the amplitude itself is called as a maximum value. So therefore r excess of 0, if substitute tau is equal to 0, still we are going to get the peak value, which is a square by 2. So therefore finally we have figured out the maximum value of the autocorrelation function is a square by 2, and it is a correct solution of this question. So now we are going to solve the 1 out of 4 question. See the question here. Assertion A. The thermal noise in metallic resistors can be characterized by Gaussian probability density function. Reason R. Power spectral density of thermal noise is essentially constant for a very large frequency range. So in the question they are given some assertion and also they are given a reason R. So we have to say whether the reason is correct explanation of the assertion or not. So out of the four options, option B, both assertion and the reason are individually true, but reason is not the correct explanation of the assertion. So let's discuss why it is like that. So first we will discuss how the noise is going to produce some power. So the noise power is directly proportional to temperature and also the bandwidth. So this noise power is going to depend upon the two parameters, which are the temperature and also the bandwidth. So if I want to remove the proportionality constant, then I have to keep a constant value. This constant K is nothing but Boltzmann constant and its value is 1.381 into 10 to the power of minus 23 joules per Kelvin. So here Pn is called as the noise power and T is called as the temperature in Kelvin. So and B is called as the bandwidth. So whenever there is a 0 Kelvin means temperature is equal to minus 273 degree. So therefore at my temperature is equal to minus 273 degree or 0 Kelvin, the noise power is equal to absolute zero value. So at this particular temperature, the noise power is always is equal to 0. So it is general thing here. So finally what I am trying to say is simply, so now suppose there are two metallic resistors. So R and RL. So RL is a communication system. Let me assume this is some communication system. So now this is called as a thermal equivalent of the thermal noise system. So this is some noise voltage. So Vn is called as a noise voltage. So because of this noise voltage, the maximum amount of noise, the maximum amount of power, noise power, which is received by the RL. So by using the maximum power transfer, the maximum amount of power or noise power received by the RL whenever the R is equal to RL. So whenever R is equal to RL, by maximum power transfer, the maximum amount of noise is going to be received by this communication load. So therefore RL is equal to R. So therefore the noise power is equal to, already we have known, which is KTB. The noise power received by this resistor is Vn square by 4R. By maximum power transfer theorem is equal to KTB. So therefore if you solve, this is called as a Vn. This is called as a RMS value. So therefore Vn is equal to under root over 4 KTB. This Vn is called as a thermal noise, or it is also called as a white noise, or it is also called as a Johnson noise. So there are different names for this Vn. So thermal noise or Johnson noise or white noise. So basically this is the RMS value, but if you want to know what is the exact nature of this, value of this thermal voltage, thermal noise voltage, which is V1 of T, it will be like this random signal. It will be a very hard to even draw. It is a random signal. We can't even exactly predict it because it is a random signal. So therefore here, suppose the amplitude at each and every time instant, the amplitude value is going to change. So I want to know with how much the amplitude is, how much probability it is going to occur. So I am going to take x-axis as amplitude and the y-axis is called as a probability. So how much probability? So for a particular amplitude, as the amplitude value goes on increases, the probability is also going to decrease. So therefore here I want to know at what amplitude, how much is the probability of occurring in this thermal noise voltage. So therefore this is going to follow the Gaussian distribution curve, or it is also called as a bell curve. So it is going to have some bell shape. So therefore this is the thing here. So finally this thermal noise, the thermal noise for any resistor, it is going to characteristic by the Gaussian probability density function. So this is the assertion. So therefore assertion is correct. So we have represented the thermal noise in terms of the Gaussian probability density function. So therefore the assertion is correct. Now let us see about the reason also. So now we will discuss about the reason. So in the reason they have given the power spectral density of thermal noise is constant for a large frequency range. This is the reason they are given. So we will see whether it is a correct or wrong. So here Pn, the noise power is equal to KTB. So if I want to divide this Pn by B, it is called as a KT. So I am going to represent with respect to theta. So this eta is called as a thermal noise power spectral density. This eta is called as a thermal noise power spectral density. So if I want to know what is the power spectral density of the thermal noise, it is equal to eta by 2. So therefore this power spectral density of thermal noise is equal to eta by 2 for a frequency of minus infinity to plus infinity. So therefore for all this range of frequency, it is going to have some constant value. So therefore the power spectral density of the thermal noise, it is a constant value which is eta by 2 for all the frequency range. Yes, the reason is also correct. But if you see the correct explanation of the reason because the thermal noise is going to have the Gaussian distribution only because of the V1 of t is a random signal and we can't predict exactly. So therefore the amplitude is going to change for each and every instant of time, and if you draw the graph with respect to the amplitude value, then we are going to get the Gaussian distribution. That is actually the correct explanation, but these two are independent statements. So we can say the assertion is correct, the reason is also correct, but the reason is not the correct explanation of the assertion. So now we'll discuss the 105th question. See the question here. The power spectral density of a signal is. So we have to know what is the power spectral density of any signal, whether it is a positive or negative, whether it is a real or complex, or whether it is a odd or even nature. So out of the four options, option B, the power spectral density of a signal is always real and even and always positive. So let's discuss why it is like this. So now we can easily correlate the power and the power spectral density. So power spectral density is equal to mod of x of omega whole square. So if you see carefully, the power of any signal, is always a positive value. So therefore the power spectral density is also a positive value. And also the power is always a real quantity. It is not a complex quantity. It is actually a pure number. So we are going to get 2 watt, 3 watt or 4 watt. So only positive 2 watt or positive 3 watt, like that. So therefore here also same thing, the power spectral density is also always real value. See, whenever the x of t and Fourier transform of x of t is x of omega, whenever the x of t is real and even, always x of omega is also real and even. So therefore if you see carefully, the magnitude value is always even value, even nature. And if you square the even nature, still it is again even, because even into even is again even nature. So the magnitude of this one is always even. So therefore if you take the square also, still it is even nature. So we can conclude that the power spectral density is always positive, always real number, and it is also have the even nature, because we are going to do the square of the magnitude. Magnitude itself, the magnitude spectrum of any x of omega is still even, and if it is a square, still it is also even. So therefore we can conclude that the power of any signal is always positive and always real quantity. So therefore the power spectral density is also positive, real, and it is even in nature. So this is the correct solution of this question. And mod of x of omega whole square is called as the power spectral density of the signal x of t. So now we are going to solve the 106 question. See the question here. SI and S0 denote the signal at the input and the output of a linear network, and NI and N0 are the corresponding noises at the input and the output. So which one of the following is the correct expression for the noise figure of the network? So in this question they are given some network. For this network, the input is a SI and output is S0, input signal power and the output signal power, and also input noise power and the output noise power, which are the NI and N0. So now we have to find what is the relation of this noise figure of this network we need to figure out. So what are the four options? Option C is the correct solution of this question. So let's solve this numerical. So this is a linear network. So here input is SI and NI and output is S0 and N0, where SI is called as the input signal power and NI is the input noise power, whereas S0 is the output signal power and N0 is the output noise power. So now we have to find what is the noise figure. Noise figure is represented by a symbol F. It is a ratio of the signal to noise ratio of input by signal to noise ratio of the output. Signal to noise ratio of input by signal to noise ratio of the output. So signal to noise ratio of input is SI by NI, and similarly signal to noise ratio of output is S0 by N0. So therefore SI by NI by S0 by N0, and if you rearrange this one, finally we are going to get SI into N0 by NI into S0. So therefore this is the noise figure for this linear network, which is SI N0 by NI into S0. This is the correct solution of this question. So now we are going to discuss about the 107th question. See the question here. Which one of the following is the available noise power produced by a noise resistor R, where K is the Boltzmann constant, T is the temperature, and B is the bandwidth? So are the four options? Option A, which is KTB, the noise power is KTB, is the correct solution of this question. So in the question they asked, if any resistor, how much amount of noise power it is going to generate? So basically we have already know the noise power is directly proportional to temperature and also its bandwidth. So if you want to remove the proportionality, you have to keep some constant. That constant value is called as a K, where K is called as the Boltzmann constant, which value is 1.381 into 10 to the power of minus 23 joules per Kelvin. So therefore if you see carefully, this Pn is called as the noise power which is generated by the noisy resistor, where T is the temperature in the Kelvin and B is the bandwidth. So therefore at 0 Kelvin or minus 273 degree, here we are going to get the noise power is equal to 0, means that resistor is not going to induce any noise power. So therefore here this also we have already know that Vn is called as, in the previous example only I have already told you that Vn is equal to under root over 4 kT Br. Here Vn is called as the RMS value of the thermal voltage. This Vn is called as the RMS value of thermal voltage, and it is also called as the thermal voltage or the noise voltage or the Johnson voltage, because it was first discovered by the Johnson, is a scientist. So on his name only they are given his name. It is Vn is called as a white noise or the thermal noise or the Johnson noise. So basically this Vn is always going to follow a Gaussian probability density function because of the amplitude values, because the amplitude nature only after amplitude what is the probability of its occurrence, all these things we are going to know only in the bell curve or the Gaussian probability distribution function. So this is the actual expression of the noise power which is generated by a noise resistor, which is KTB, is a correct solution of this question. So now we are going to solve the 108th question. See the question here. If two resistors of values R1 and R2 at temperatures T1 and T2 are connected in series to form a white noise source, the equivalent noise temperature is. Suppose there is a two resistors which are connected in series at particular temperatures of T1 and T2. So now all this equivalent is going to have a how much amount of noise temperature that we need to figure out, or the equivalent temperature we need to figure out. So the four options, option A is the correct solution of this question. So let's solve this numerical. So in this question they are given that resistors are connected in series of resistor R1 and R2 with the temperature of T1 and T2. So this is equivalent to this. Whenever the two resistors are connected in series, the equivalent resistance will be summation of the each individual resistor R1 plus R2. So we have to find what is the equivalent temperature we need to figure out. So here we have already know the thermal noise voltage is equal to under root over 4 kT Br. So I am going to take now square value. So which is Vn equivalent square. So I want to know what is the Vn equivalent square is equal to 4K. So which is T equivalent and R equivalent. So therefore T equivalent to R equivalent, and remaining everything is constant. For 4K B is constant. The only variable parameters are the equivalent resistance and the equivalent temperature we need to figure out. So therefore similarly for the first resistor, same thing here, Vn1 whole square is equal to 4K T1 B R1. For the second resistor, the thermal noise voltage square is equal to 4K T2 B R2. So therefore the total thermal noise voltage will be summation of each and individual one. So therefore we know the value of Vn equivalent square, substitute that value, and also we know the value of Vn1 whole square, substitute that value, and we also know the value of the Vn2 whole square, substitute that value. So therefore here 4K B is a constant value, the only variable got temperature and the resistor. So if you solve this one, we are going to get finally that T equivalent is equal to T1 R1 plus T2 R2 by R1 plus R2, because R equivalent is equal to R1 plus R2. So in place of R equivalent, I am going to substitute R1 plus R2. So finally I am going to get T equivalent is equal to T1 R1 plus T2 R2 by R1 plus R2. So we can conclude that the equivalent temperature of this series resistor of these two resistors is equal to T1 R1 plus T2 R2 by R1 plus R2. This much amount of temperature rise is going to occur whenever we are going to connect these two resistors of individual temperature and T1 and T2. So in the previous case, I think you are confused why I have used this like this. Vn equivalent square is equal to Vn1 square plus Vn2 square. Why I use like this? Because here the noise power is equal to KTB. So here Pn is equal to, generally we know the value of the power. Power is equal to V square by R. So therefore total power is equal to summation of each individual power. So therefore, but here in the noise resistor, that noisy power is depending upon only temperature and the bandwidth, but it is independent of the resistor. So therefore we can conclude that this is directly proportional to only the square value of the noise voltage square. So therefore this is called as a Vn equivalent square is equal to Vn1 square plus Vn2 square. So this is the reason I have used this equation, because here the noise power is only depending upon temperature and the bandwidth, but it is independent of the resistor. So I have to remove this resistor. So therefore it is directly proportional to the square of the thermal noise voltage, because we have already known, because the temperature is nothing but here Vn is equal to under root over 4K TB. So therefore here Vn square is equal to 4K TB. So therefore temperature is directly proportional to Vn square. So therefore as the power is directly proportional to temperature, so therefore power is also proportional to Vn square. So by using this formula only we have did this one. So total power is equal to summation of individual power. So by this we have known the Vn equivalent square, Vn square and Vn square. So substitute those values, and then finally we have got T equivalent. The equivalent rising temperature is equal to T1 R1 plus T2 R2 by R1 plus R2. So now we are going to solve the 109 question. See the question here. Consider the following statements. The thermal noise pore generated by a resistor is proportional to. The thermal noise pore generated by a resistor is proportional to the value of the resistor, the absolute temperature, the bandwidth over which it is measured, the Boltzmann constant. So which of the statements are correct? The four options. Option C is the correct solution of this question. So let's solve this question. See, I have already told you about the noise pore. The noise pore is directly proportional to temperature and the bandwidth. So therefore, if you want to remove the proportionality constant, you have to keep some constant, which is K. K is called as the Boltzmann constant, and T is called as the temperature in Kelvin, and B is called as the bandwidth, where K is the Boltzmann constant and Pn is the noise pore which is produced by the resistor. So if you see carefully, this noise pore is going to depend upon only temperature and the bandwidth. Only these two are the parameters. Only on these two parameters the noise pore is going to depend. So therefore we can conclude that it is a constant. So therefore the noise pore is independent of the constant, and also the noise pore is independent of the resistor also. So that is the reason the noise pore is directly proportional to temperature. So you can see the noise pore is directly proportional to temperature, bandwidth is constant, and the temperature is directly proportional to the square of the noise voltage square or thermal voltage square. So by this relation only we have used in the previous example. So therefore we can conclude that the noise pore of any resistor, of noisy resistor, is going to depend upon only two parameters, which are the temperature and the bandwidth, and it is independent of the resistance value, its particular resistance value, and also it is independent of the Boltzmann constant, because K is only a constant value, so it is independent of that also. So therefore we can conclude that the noise pore is depending upon only temperature parameter and the bandwidth parameter. Now we are going to discuss the last question of this lecture. If ACF denotes the autocorrelation function and PSD denotes the power spectral density for white noise or thermal noise or the Johnson's noise, ACF is. So we have to know what, suppose in the question they are given that ACF is autocorrelation function and the PSD is power spectral density for white noise. So what is the nature of the ACF and what is the nature of the PSD? We need to figure out. So what are the four options? Option B is the correct solution of this question. Means ACF is a delta function and the PSD is a uniform function. So let's solve this numerical. So here R of t is called as the autocorrelation function and S of f is called as the power spectral density. And if you take the Fourier transform of the autocorrelation function is called as the power spectral density. So here Pn is equal to KTB. I have already told you this one. So if I want to divide this Pn by B, it is nothing but KT, that I am going to assume as a eta. So eta is called as a power spectral density of thermal noise. So therefore here R of t is called as the autocorrelation function and S of s is called as the power spectral density. In the previous example only I have already told you that here this S of f is always eta by 2 for minus infinity less than or equal to f less than or equal to infinity. So I want to know what is the nature of this R of t. So therefore already I have told you the Fourier transform of the R of t is equal to S of f, means the Fourier transform of the autocorrelation function is equal to power spectral density. So now I am going to assume this is eta by 2 delta of t. So eta by 2 delta of t is equal to S of f. I want to know what is the nature of the S of f. So Fourier transform of the delta of t is again unity. So therefore this is a constant value. So therefore eta by 2 is equal to S of f. So we have know that the power spectral density is eta by 2 for minus infinity less than or equal to f less than or equal to infinity, and this autocorrelation function is that eta by 2 is delta of t. So we can conclude that ACF is a delta function. So ACF is a delta function, whereas the PSD is a uniform function, means it is going to have some constant value, because if you draw the graph here S of f, if you draw the S of f, it is a constant value for all frequency, which is eta by 2. So we can conclude that this is a uniform function. So therefore this is a uniform function. So we can conclude that Fourier transform of the autocorrelation function is equal to power spectral density. So therefore the autocorrelation function is always a delta function, whereas the power spectral density is always a uniform function, means it is going to have a constant value for all frequency. So this is the correct solution of this question. So by this lecture we have successfully completed the 110 questions which are the previous year IES or ESE questions of the communication systems of prelims in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever you upload a new video, direct notification comes from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So thank you so much for watching this lecture. Keep smiling, take care, and bye bye.